was that while initially we may look at just X and Y on its own, we may say we had no information, but once we look at how it reacts with our alkene, we could come up with predictions about the partial charges on those atoms, X and Y. And I already forgot what they were. It looks like the Y was negative and the X was positive. And that's based on seeing where those atoms went in the product. So if Y is negative, that means what charge would I expect on that carbon? That carbon should be positively charged. Okay? And to decide if that carbon is best to be positive, we would have to go through and evaluate the resonance structures from our alkene. And we should verify in all cases that we do end up with two possible resonance structures and the positive charge is best found on the most substituted carbon. This allowed us to backtrack in saying what X and Y were. Okay? So all of the reactions that you're dealing with additions or alkene additions, you're adding X and Y across the double bond. Okay? All we're doing is changing the identity of what those X and Y's are. You need to know what the positive and the negative are, and in some cases it's more obvious than others. So let's pick a couple examples. Let's start with the middle one straight up the top. Okay? What happened in this circumstance? What's our positive? What's our negative? What's the X stand for in this case? A halogen. So we could pick an example, HCl. What's our positive? What's our negative?
CL is negative.
Cl is negative. H is positive. Where did we put the negatively charged atom? We put it on the most substituted position of the double bond. Okay? So it follows that pattern. You could go through and do that with the H3O+, but I'll tell you it's the same thing. Go through and do that again with the alcohol there. Again, it's the same thing. In each of those cases, what we're identifying as the positive atom is H+ in each of those three cases. Okay? So that's our pattern we're putting in the negative for the other one. There's some of these that are less obvious. Okay? For instance, we could shift to the palladium one to the right. Okay? Our platinum and palladium. What's our positive and negative in that case? What reagent are we adding across the double bond? What atoms? Hydrogen and hydrogen. Which atom's positive? It doesn't really matter. They're both hydrogen. Okay, but we're still putting a positive and a negative across that double bond. Okay, the platinum is what's facilitating it. Why do we need the platinum? Okay, how small is hydrogen? Really, really small. So small that it can't really coordinate well with the double bond. Okay, well, if it can't get in and interact with the double bond, we don't see a reaction. So we have to add something to facilitate that interaction, getting those electron clouds to overlap to allow for the reaction to occur. Okay? What happens if we shift to Br2? Okay, this reaction. What's our positive atom? Bromine. And our negative? Bromine. Now, this is very, very similar to the hydrogen one. Okay, but why is there no catalyst in this case?
Not necessary with bromine.
Why is it not necessary with bromine? It's true. Bromine is huge. It is so big that we don't need something to facilitate getting those electrical or those orbitals to overlap. Okay, so bromine can directly interact with it and we can put that bond on there. Okay? You'll notice that we do see some differences in the dynamics of each of these reactions, and a lot of that comes back to the mechanism. How do you know the mechanism? There's two ways. One, you go into lab and you figure it out. You test it. Or two, you trust that somebody else went into the lab and they told you the answer. Okay? All mechanisms that you're dealing with, all of these results are based off of some lab system. So to a certain extent, we do have to memorize these, okay, within a certain extent. But we can come up with predictions within each of these as well. and use those predictions again and again to try and manipulate what's going to happen in future circumstances. Okay? What about the next two underneath bromine? Switch it up to origin. Both of those involve bromine, but we've added something else into this. What's that something else? Water in one case. The other case, it's technically an alcohol. What's the negative in this case? Oxygen. Bromine starts as the positive. Okay, it's the one that polarizes and reacts with the double bond. Okay. The last three examples that we've got up there are using boron or mercury with those reagents. The mercury one, for some reason, is not in the Smith textbook that I can find easily. The only reason it's really mentioned is because of that lower left-hand comment. There is no rearrangement possible. Okay. Well, yeah, we could look at that rearrangement, but aren't those two products unique? I mean, I've got a whole arrow coming out to those. Why would I draw a product a second time? Is there another reagent that generates those exact same results? Yeah. Acid in water or acid in alcohol. They do the exact same thing. Those were the two up at the top. Okay? So those do effectively the same thing, except in the reaction with the acid, we form a carbocation. What's the issue with carbocations? They can rearrange. So if I do not want a rearrangement, I need to go through and use the mercury or find a different reaction altogether. Okay? So when would the circumstance be where I don't want a rearrangement? We always come up with this hypothetical. If I don't want this to happen, then I have to do this. Okay? What am I saying when I say I don't want this to happen? I'm trying to make a molecule. I'm going into the lab to make something, to make a drug, okay, to make a particular molecule. That's what we're trying to learn here. We're picking up the reagents so that if we go into the lab, we can start to predict and make things into larger pieces. This is why synthesis becomes more and more important as we move through second semester. And you won't be expecting to just predict one product. You'll have to string together 3 or 4 reactions to predict a new product at the end, okay? An actual real target. Yes? No? Okay. Boron is kind of off on its own as an interesting thing. I like to talk about boron a little bit, though. What's the positive in that reagent? It's the boron. Boron's neat because of its location on the periodic table. It's happy with just 6 bonds. If it's got, 3 bonds, 6 electrons, which means its hybridization is sp2, which means there is a leftover p orbital. And what can we slide into that p orbital? Electrons. In this case, those electrons are coming from the alkene. Okay? That structure very quickly adjusts itself, and one of those hydrogens on the boron gets dumped in as the negative charge. Okay? That's why this reagent is kind of fun. Okay? Because we end up putting in a negative hydrogen, which we've already talked about is ridiculously unstable. It is ridiculously unstable. Boron stabilizing it. Okay? Once we've put the boron on, though, we now need to get it off. How do we get it off? Step 2. Step 2 comes along and kicks off that boron reagent and leaves us with the alcohol. Okay? So it's looking at why we use each of these reagents and try and slide them back into that previous situation of our X and Y and our alkenes and trying to find these patterns. If you don't want to find the patterns, that's fine. Just realize what you are now trying to do is just memorize everything. It's legit. It works. Yes?
Does that mean that these 2 reactions the product can be rearranged? Or we have 2
those,
products with a major?
with those 2 reactions, so what
We have no mercury?
we is talking about is these guys up here,
Yeah.
those 2 reagents can form or can undergo rearrangements.
Okay.
Okay? So what you would do is run the reaction and see what happens with the carbocation. Where is the carbocation formed? If it is formed on a stable tertiary carbon, should it rearrange?
No.
Because
It's stable.
it's stable. There's no reason to rearrange. If, however, that carbocation forms on a secondary carbon, what happens? It may rearrange. If we have one position of one rearrangement shift, can we put the carbocation on something more stable? And if we can, then yes, it does the rearrangement, and we expect that product as the primary product.
Okay. I mean the majority.
The majority, yep. Yes.
Would we expect a rearrangement like the one with the OH coming out of the other, the one like with the boron example?
The boron example does not form a rearrangement either, and the reason being, again, no carbocation. So when we're doing our acid reactions, slide this, come on. Oh, that red arrow doesn't work. If we look at all of our acid reactions, all of those form a carbocation intermediate. With that carbocation intermediate, you can get rearrangements. Okay?
So as long as they all rearrange.
Yep. The other ones won't rearrange because we don't form a carbocation. These reactions also apply to your alkynes. You get pretty much identical results with the alkynes. There is some extra chemistry that pops up with your alkynes, and that has to do with, let's see, do I have a, shoot, there's not a nice example there. So let's draw one in here. Your alkyne, particularly terminal alkynes, the hybridization of that last carbon is sp. What happens is we reduce hybridization. Becomes more s character. Where's the s orbital relative to the p orbital? Closer to the nucleus, which means the electrons are held closer to the atom. Do we have a way of ranking elements based on how well they hold their electrons? Say bromine versus hydrogen. Yeah, electronegativity. When we shift to an sp hybridized carbon, its electronegativity effectively goes up high enough that that hydrogen now becomes acidic. And if we use a wicked strong base, what we can do is remove that hydrogen, and we end up with what's referred to as the acetylide ion. What's nice about an acetylide? Negatively charged, it can react with anything that's possibly positively charged. So when we take a look at the upper two on the left, both of those start with a base. Why? That base is reacting with the acetylene to make the acetylide. Once we've got that strong nucleophile, it can then react with, what do nucleophiles react with? Electrophiles. So if we take a look at those two upper cases, where's our electrophile in that reagent? What's the electrophilic atom? It's our R group, which is probably a carbon. Why? What's the X typically stand for? It's a halogen. Why is the carbon the electrophile? Halogens are more electronegative than the carbon. They've pulled that electron density away. That carbon becomes positive. There's your electrophile. What about in that other one? Where's our electrophile here? It's the carbon again. Okay? It's an interesting one. Why? Have we talked about that functional group yet? We haven't talked about our ketones or carbonyls. Why is that carbon partially positive? Because oxygen is more electronegative and is withdrawing that electron density. Okay? So if you can pick out your positives and negatives, it does follow kind of nicely through it. Okay? The standard reagents that we won't address here, these guys are all, oops, shouldn't have looped that, are all effectively the equivalents of your alkenes. Nothing particularly special or different about those reagents. They go through and do the exact same reactions as you would see for your alkenes. The one caveat is that we can do it an extra time. We can do it twice. Why can we do it twice? There's 2 pi bonds. Okay? 2 pi bonds, I can react each pi bond with each of those reagents. Okay? The last 2 look a little bit weird. Why do those look weird? What functional group have we formed? We got a carbonyl. We haven't seen that really happen before. We will talk about those in depth. I make the very strong argument that we get the exact same results as we would expect with the alkenes. With the alkene, when we reacted our boron, what did we do? We put an oxygen where? On the most or least substituted position. With the boron, it went on to the least substitution. So we added hydrogen and an OH across the double bond where the oxygen went on the least substituted position in the anti-Markovnikov fashion. Okay? What happened when we used our mercury? Where did we put our oxygen? On the most substituted. If we go through and take a look at these 2 reactions, where did the oxygen go in our boron example with alkynes? The oxygen went to the least substituted carbon of the alkyne. Notice it's got the hydrogen coming off of it. It went to the carbon at the very, very end. If we take a look at our mercury reagent, where did the carbonyl, or where did that oxygen form a bond? On the most substituted carbon, towards the middle of the structure, hence there's 2 carbons attached to it. Okay? Why on earth do we end up with these carbonyls and not just the H and OH added across to it? Okay, I'm going to need a new place to actually draw here. And of course it left everything. If we just add our H and OH across our double bond, or our triple bond, sorry. Let's just put an R group out here. And we'll call this, I'm just going to say boron, B for boron, 2 with our peroxide step for P. We do form this product, okay, exactly as we would have predicted for the alkene. But this structure is a bit odd. Okay? Is it strictly an alcohol? For it to be an alcohol, we have to have an OH attached to just a standard sp3 carbon. Is that carbon sp3? Nope, it's sp2. Is it just an alkene? For it to be just an alkene, we should really just have a carbon-carbon double bond that's connected out to other carbons or hydrogens. Nope, I've got an OH sitting out on it. The proximity of those 2 functional groups changes the overall chemistry, and what ends up happening? The lone pair comes down to form a new pi bond, which we then have to break that bond to pick up NH+. Sorry, that wasn't meant to be a squiggly line. Does the oxygen want to remain positive? What happens? Steals the electrons from the hydrogen. The net result, we've ended with our carbonyl. Okay. That process is very commonly referred to as resonance, which is wrong. It's not resonance because we've changed the location of an atom. What atom did we effectively change the location of? The hydrogen. It went from being on the effectively 1 position to now becoming on the 3 position. Okay. Because we've changed the location of the atom, it is no longer resonance. What we're looking at is what's known as a tautomerization. This tautomerization is ridiculously important. We're going to see it a lot towards the end of the semester. When we look at what functional groups? Carbonyls. Yes, sorry.
I was wondering, what was the P in 2 there?
P was peroxide. I knew I should have written those out. So our B equaled our BH3 with THF. The P come on, P equals a peroxide, H2O2. I would have written them out up there, but I'd already canceled all my space. Okay, other questions? Okay, good, that was 15 minutes on all review stuff. Chapter 12, alkenes, reduction and oxidation. Not the entirety of chapter 12 is on alkenes. The last, I think, 2 or 3 sections look at oxidation and reduction of alcohols, which we'll look at whenever we talk about alcohols. Okay, so just be aware of that. Within this chapter, you've got a bunch of reactions. Typically, what we're looking at are adding oxygens to these. There is a reduction, which I did not show up there. What's the result of reducing an alkene? An alkane. We just added hydrogens to it. So that reaction was actually in one of the previous slides. Okay, so all of these are actually our oxidation reactions. We will talk about in more detail this branch, okay, our MCPBA forming the epoxide. Okay. Why might we be looking at those branches a little bit later in the semester? The end result is what functional group? Alcohols, also to be discussed later in the semester. Okay? Those of you that had me for first semester, we talked about those already. I didn't go into a lot of detail because I knew I was going to talk about them now. Okay? The other reactions, if you want to look at mechanisms behind those, I can help you with mechanisms for most of those. Pretty much all of them, but for the most part, you just kind of have to have them memorized. Okay? So there's some characteristic things that show up with those reagents, but for the most part, it's just going to be a lot easier to memorize them. The main reason being, pretty much as soon as you bring in a metal, all things go to hell. Okay? And that's because metals bring in d orbitals, and we're organic chemists. We tend to get confused with letters that come after P. As far as the alphabet of atomic orbitals go. So some people got that. Remember, S, P, D. Okay. Side point. So, I said I wanted to take a closer look at one particular reaction. So this is off of the slide that we're looking at for chapter 10. And this is really our radical reactions. Okay? So what happens if I take this reaction, but instead of using the HBr, I just add the radical initiator. So our radical initiator is that ROOR. Okay? Well, one possibility, well, we don't get a reaction. You get rid of one of the reagents, we can't get the reaction. Okay? And this is where second semester becomes a bit of a bear. In this case, we do get a reaction. This reaction forms this massively long product, and this reaction will continue to go on and on and on, which is what those parentheses are trying to, or that end bracket is trying to represent. That our structure is going to repeat on and on and on outwards. Okay, that same pattern all the way through. Question becomes why? If I just have peroxide and the alkene, where did all those other carbons come from? When we run a reaction, do we start with just the peroxide and just one alkene? No. We have probably orders of millions of billions or trillions of these molecules floating around. Can an alkene potentially react with an alkene? Absolutely. Okay? So if we look at the radical initiator, what ends up happening is we form our new radical. That radical can then react with another alkene in a radical fashion, and we can repeat that, okay, until two radicals impact each other in what is known as the what step? Termination step when we're looking at radicals, and we would end our polymer. We will look at polymers at the end of the semester, okay, but I wanted to bring this up now because there's another way we could have done this. We didn't have to have a radical initiator. We could have done this in this other fashion, where we have one alkene attack the next. And you'll notice that if we go through and look at our alkenes, the way I showed this was one negative attack another positive. How do we know we have these partial charges? What happens when you draw the resonance? When you draw the resonance, you see the positive charge is better on the more substituted position. Once we've done this once, we now have a structure that has two ions. Does it want to be charged? Nope. So it seeks out another molecule to try and cancel that charge. When we're looking at radical reactions, we don't see a whole lot of positives and negatives floating around. So the most likely thing that those molecules will encounter will be another neutral alkene, and the polymer chain grows. Until eventually, what ends up happening is that we have no more alkene, and now we've given our charges enough time where they could potentially interact with each other and either loop back on each other or terminate the chain. Okay? So, why go through all this? I want to see that those alkenes can react with alkenes. It's really what chapter 16 is looking at. Okay? So let's take a look at some other alkenes. Okay? In this case, I've decided to string them together into the same molecule. So I'll give you 5 minutes to kind of work on this. This is really 6 questions. So take each of those reagents and react them with one equivalent of HBr. So if I react one equivalent, how many hydrogens should add to my structure? 1. Okay? How many bromines? 1. Question is, where? Okay? The next part of it would be polymerization conditions. Okay? I will grant you the polymerization conditions are awful to draw those products out. So if you can kind of think about that rather than draw it, that's probably the best bet. Okay? I'll give you 5 minutes. Okay, let's pick it up. So with that first one, hopefully we got something like that structure drawn. Why did I pick the rightmost pi bond?
It wouldn't matter.
Doesn't matter. Okay? Either way we put it on there, first off, we'd end up with the same product, but taking it a step further, is there any difference between those double bonds? No. So even if we froze the structure and said, don't move it, now they don't overlap, it's still no difference between those products. They're at the exact same energies. If we go through and move to the next one, now we see something interesting develop. We do have the possibility for now a different product coming out of this. Okay? And the question becomes why? Why should a different one show up? Has to do with the carbocations that form. Okay? I picked the leftmost carbon to be the most reactive. They're both pretty equivalently stable, but in general, when we're looking at reactivities with HBr, we're looking at the most substituted alkene reacting because in general, that makes the most stable carbocation. Okay? In this case, the carbocations are relatively close in energy depending on either one of those double bonds. Okay? So I could just add HBr across the double bond, the leftmost one, and end up with the result that I drew first. Okay, where I put the hydrogen on this carbon and the bromine on that carbon. Did I have to put them on in that way? Couldn't I have put the hydrogen there and the bromine here? Both those structures end up with secondary carbocation intermediates. Why is the red answer better than the blue answer? Why is it more stable? And I'm hearing the word coming out there too, allylic position. What we're referring to is the carbocation that is formed through the red addition puts the carbocation at that position, which is resonance stabilized by the pi bond. If we looked at the blue structure's intermediate, is that carbocation stabilized? Nope. Without that further stabilization, that structure is not as stable and reverts back to its starting position relatively quickly, and we don't expect to see that blue product show up to any significant extent. Okay. You'll notice that one option as well, which I started to draw in the red case, is I could have gone through and done that resonance result, which would yet again give me another product. We could put the bromine, let's put the positive charge there first. Could have put the positive charge out there and put the bromine out there. Why not show that product?
That's even less stable.
It's less stable than our secondary carbocation that we had from the initial one. Okay? In that last reaction, we've added yet another double bond to this overall structure, and we end up with, again, more possible products coming out of this, because each of those double bonds can go through and contribute to varying extents the overall stability of those intermediates and products. Okay? We'll end up with even more than that. Okay? Kind of get the idea? If you draw an intermediate, always check for resonance. Okay? And this is one of the cases where the ACS test tends to hit people that just memorized. If you just went through and memorized that HBr adds to a double bond, you may only end up with one product. And the ACS will say, well, actually, there's 3 possible ones. If you don't know that you've got that intermediate with the carbocation that does that resonance sharing, you're kind of dead in the water and you lose that answer. So every time you draw out a reaction, it's helpful to know those mechanisms. Okay? So remember kind of those caveats within each of these. Okay? The real part that I wanted to get to was actually the under polymerization conditions. And that first one, we're just going to see a result of just a nice long carbon chain. Because those double bonds never really interact with each other, we're not going to see anything different than that. Okay, we'll just end up, with each of those carbons, each of these chains polymerizing. And I'm going to turn that a little bit so that they don't encounter each other. So we could polymerize outwards from that point. For the second one, we could do the same kind of thing. We can get polymers running across. But just as easily, we could polymerize within that same direction, and our double bond could end up in the middle, and our polymer run outwards. 1, 2, 3, 4, 5. Yeah, and then I think that runs outwards. Okay, so we could keep the alkene depending on how the polymerization worked. Okay. The last one, we could end up with a similar result, and this is really the one that I wanted to get to. I would argue that we do end up with the possibility of this product. How did that happen? Alkenes can react with other alkenes. Okay, we usually see them reacting with other structures because it's usually easier to bring 2 structures together. What's special about that last case? It is now long enough that if I fold it up appropriately, the snake head can eat the snake tail, and we end up cyclizing that structure. Okay, so if we redrew that, actually, did I redraw it somewhere? There I did. If I redrew that structure and flipped it around, you can see that that is a possibility. And what ends up happening is the pi system from 1 shifts all the way around. Okay. This is a whole secondary section of material that we could go through and discuss. Again, it's not in the textbook, and it doesn't really fit into our course competencies. So we'll kind of just gloss over that and recognize that what we'd be looking at with these types of reactions are cycloaddition reactions, and they're really cool because we can use molecular orbital theory, which you all learned in general chemistry, right? Probably not. Okay? So with molecular orbital theory, what we'd end up doing would be combining atomic orbitals to make molecular orbitals, much like hybridization, except in hybridization theory, what we ended up doing was just saying, oh, I'm going to collect them and make them. I don't really care about it. Molecular orbital theory, more appropriately, is the linear combination of atomic orbitals. Right? So the Lakow molecular orbital theory is the mathematical version of that. The reason that method gets used is that allows us to predict a lot of potential reactions like this one, and in particular the stereochemistry that comes out of it. Okay? The reason why we're addressing it now is just mention that it does lead us kind of nicely into the Diels-Alder reaction. Okay? So let's, before we move too much into the Diels-Alder reaction, let's look at the molecular orbitals for our Diels-Alder reaction. Okay? What orbitals are we concerned about within our Diels-Alder? So what atomic orbitals? We've got p orbitals. We've got the p orbitals that are changing, okay, their orientations at each of those carbons. Okay, so that's 4 atomic orbitals that are being manipulated. They aren't really atomic, though, because they're in a molecule, so they're molecular orbitals. So what we're going to go through and do is take a look at each of those atomic orbitals and look at how they can relate with each of the other atomic orbitals to generate molecular orbitals. Much the same thing as we did with hybridization theory. Okay, with hybridization, we knew we needed 4 hybridized orbitals to make carbon for CH3 or CH4 to get those 4 bonds. So what did we do? We took our atomic orbitals. Which atomic orbitals? The p. How many p's for a tetrahedral carbon? How many p orbitals are there? 3 p orbitals, which gets us 3 molecular orbitals, but if it's tetrahedral, we need 4. Where's that 4th orbital? The s. What do we call that molecular orbital? sp3, because it represents each of the orbitals that came into it. Okay? When we're looking at the linear combination of atomic orbitals, we're doing something sort of similar. Okay? In this case, we're going to look at the p orbitals involved in making that structure. Okay? So I'm going to arrange those p orbitals in that general structure, and you notice that I've rotated it so that we match up a little bit nicely. Well, if I start with 4 atomic orbitals, how many molecular orbitals should I end up with? Let's go back to our tetrahedral carbon. We took in 1 s orbital, 3 p orbitals. How many molecular orbitals did I get out of that? 4. How many atomic orbitals did I start with? 4. Okay? We have to end up with the same number of molecular orbitals as we did atomic orbitals. How many atomic orbitals went into this? 4, which means we need 4 molecular orbitals. So let's go through and look at the possible molecular orbitals. When we have a p orbital, okay, they're in opposite phases. Each lobe has a particular phase associated with it. How is that phasing typically represented? Anybody remember? We could try it with an arrow. That's an interesting idea. I actually haven't seen that one. It's usually shown with shading. Usually different colors. I think your textbook shows it as blue and green. In this case, I'll just go through and color one in and leave the other one empty. Okay? If we're going to look at our lowest energy orbital, so that'll be the one at the very bottom of this. Okay? Lowest energy is going to mean what? What's happening with our orbitals? Maximum overlap or minimum overlap? Maximum overlap. So I want to make sure each and every single one of these orbitals overlaps each other with the exact same phase. So I can go through and color them in like so. Did I have to color all the top? I could have colored all the bottom. It's the exact same result. Okay? If we move up in energy, there has to be a reason we're going up in energy. Well, that reason is that we've added a node. Okay? A place where electrons cannot exist. Same thing happens when we look at atomic orbitals. When we go from s to p orbitals, what happens to the shape? We get a little dumbbell, a little point in the middle. What's happening at that point in the middle? That is a node. That is where electrons cannot exist. So what we now want to do is add to our structure, go through and again work through the shading in such a way where we've put a single plane where we do not get this overlap. Well, there's overlap, but here I'm going to switch it. Now I'm going to shade the bottom. I now have a node running right through the middle of the structure where the orbitals do not overlap with each other. What happens if I move up further in energy? I now need how many nodes? 2 nodes. So we'll again go through. Whoa, come back here. And now I've got a node running through that side and through that side. So 2 nodes. How can I get 3 nodes? Every other one. I now have, did I do that one right? I think I did. I now have my molecular orbitals for my Diels-Alder reaction. If I want to see how this is going to interact with the next molecule, I also need to know where the electrons exist. How many electrons are going into each of these orbitals? We can represent it with a line. There's an orbital, there's an orbital, there's an orbital, there's an orbital. How many electrons can I put into an orbital? 2. How many electrons should I be adding to this molecular orbital diagram? 4. Why 4? What orbitals are we looking at? The p orbitals. Because we're coming from a starting carbon atom, how many electrons does that carbon atom put into that individual orbital to generate this? Only 1. To form the pi bond, what happens? The other carbon contributes. So we bring in 4 electrons. Where do we put those 4 electrons in this situation? Okay, one option, 1 in each. Does that make sense? No, why not? Lowest energy first. So we'll go 2 into the lowest. That's full, so we move up to the next one. 2 in that one. We now have an orbital diagram for this molecule explaining how the electrons are scattered through the pi system. Okay? I now want to see how it could potentially interact with the next molecule. And this is where I'm going to be very upset because all my shading is going to disappear. Okay, so remember the shading within this. So we can bring in the next one. You'll notice this one's going to be a lot simpler because we only have 2 carbons. Okay? And if we went through and shaded this one, the lowest energy one would look like what? Whoops. That was the wrong button, but it's good enough. We can go 2 on top, 1 there, 1 there. Okay, and then I'm going to go through and shade this guy back so we can see it. Okay. We have 2 electrons to dump in for that second situation. Those 2 electrons are going to go into that lowest orbital, just like we did with the other circumstance. If I'm going to have these 2 molecules interact with each other, okay, they need to now share electrons between them. Okay. Which one of these molecules do you think is most willing to give up electrons? The one with more electrons kind of makes sense, right? It's already got a whole bunch. So let's have it dump electrons and share with the other one. Okay, to do that, where do the electrons go? What's that? Which orbital do they move into? They'll move into the unoccupied one. Why would they move it into the unoccupied one? The other one's already got electrons. It's already occupied. So what we're looking at is interacting the highest occupied molecular orbital of one situation and the lowest unoccupied molecular orbital of the other. That's an awful lot of words. So what we end up calling these would be the HOMO and the LUMO. Okay. How can this be further helpful for us to actually see that this reaction works? Look at the HOMO and the LUMO. Evaluate those 2. For this reaction to occur, let's take a look at our far product. We're forming 2 new sigma bonds. Okay? And we could go through and do the exact same thing that we did with our p orbitals, except now our sigma bonds look slightly different. We're looking at overlapping orbitals. Our lowest energy situation is going to be what? The orbitals overlap, okay, where they're in the same phase. There is a little bit of shading associated with it, though it doesn't look very nice, so we can color that in. In our lowest energy situation, those are all in the same phase. In our highest energy situation, they are out of phase. So in the highest energy situation, what we would have is a sigma antibond, or the sigma star. So it's not forming a bond. Well, if I want to form a bond, I want my orbitals to be in the same phase when they go through in a line. Take your HOMO orbital and your LUMO orbital. Take a look at the atoms that are actually forming that bond. Can we set it up so that they are in the same phase? Yep, we can. If we tried the HOMO-HOMO, would that have worked? So in the case of our diene, our 4-carbon one, they're on opposite sides, right, our shading. We take a look at the HOMO of our Dienophile. Are they on opposite sides? No. We can't possibly interact those two orbitals because the orbitals don't result in an overlapping situation to make the overlapped sigma bond. Okay. Sorta, kinda. Sorta, kinda is good enough as far as we need here. So what we're looking at is those p orbitals, how they interact with each other, and how they can go through and generate these products. The typical names that come out of this is a HOMO-LUMO interaction. Did it have to be the HOMO of our diene and the LUMO of our Dienophile? What's the other interaction, Sarah? We could have taken the HOMO of, go through in purple, if we take this guy's HOMO and we match it up with this LUMO, do we see that interaction being favorable? Yeah, we could potentially overlap those orbitals to form that sigma bond. Okay? Which one is better? They're both about the same. Okay? One is more favorable, and if we really wanted to get into it, we could. I don't think you really want to get into it. Uh-oh, there's a hand. Does that mean you want to get into it? What's up?
I have a slightly different question.
No, that's fine.
How come the HOMO of the diene? Is that the two?
The diene is the one on our left.
Okay. How come the bottom one of that one couldn't interact with the HOMO of the, what's it called again?
Dienophile.
Dienophile, okay.
Interesting question. Why not?
Because it looks like they would match up to me, at least.
I agree. That's true. Why is that a bad interaction? Why do I not take... Oh, I've already got purple in there. Let's try orange. So what you're saying is the HOMO of the Dienophile coming in orange, that orange box, yes? And the bottom one of our diene. Why do we not see that generating our bond? So we could make an argument with that. If we're going to go through and do a reaction, okay, we're going to react our highest energy things first so we can get a lower overall energy. Okay? So that's a good explanation. I can accept that. Within those two orbitals, is there a space to get those electrons to match up? No, those orbitals are already full. There's no way I can spread those electrons across it. Okay? That was the argument I was thinking of. So Megan, that was a good one. Okay? So we can look at these energetics and we can look at the potential of putting electrons in. Okay? Other questions on that? So the big terms that are going to come out of that are HOMO and LUMO. Highest occupied molecular orbital, lowest unoccupied molecular orbital. Yes?
And the sigma star doesn't get formed.
And the sigma star we don't want to be formed. If the sigma star forms, that's an anti-bonding orbital. That prevents the bond from occurring, hence the anti-bond, like matter and antimatter. As soon as we bring them both into the same situation, boom, we lose it. Okay? Yes?
So that means we have the LUMO of the diene, okay, and interact with the HOMO of the Dienophile?
That is one possible interaction, yes.
Or these two?
Or the HOMO of the diene and the LUMO of the Dienophile. So it's always going to cross.
They go like this, or they go like this?
It goes like this and like this.
Oh, okay. Why they don't go like this?
Why does the LUMO of one orbital not interact with the LUMO of the other orbital?
They're on unoccupied.
They're both unoccupied. If we're going to form a bond, what do we need? Electrons. So why not have the LUMO interact with the LUMO?
But they have no.
There's no electrons. We can't form a bond if there's no electrons to put in there. Okay? So we'll kind of step away from those, and in 5 minutes I'm going to cover the next 15 slides. Don't worry, I won't. What changes occurred? So those of you in lab can help us speed through some of this. What things happened in the course of the Diels-Alder reaction? We formed 2 sigma bonds. Okay, that's the end conclusion of it, but it does seem like a lot of other things happened as well. We could go through and say, well, we broke all of those pi bonds, and we formed a new pi bond, and we formed those new sigma bonds. Okay? The reason we can skip looking at the pi bonds is because of resonance. Because I could just as easily draw this structure out with just sigma bonds and no pi bonds by putting in those charges. So really, the pi bonds aren't changing. This means only 2 things happen. Okay? What we're looking at is the formation of 2 sigma bonds. And what we're going to be concerned about with the Diels-Alder reaction is when do those 2 things happen. Okay? So that when is what I'm labeling as DA1 versus DA2. DA for Diels-Alder of type 1, not unimolecular, just type 1, and Diels-Alder type 2. In the Diels-Alder type 1, we're going to make the first sigma bond, and then we'll make the second. In DA2, we'll make both sigma bonds at the exact same instance. We should see parallels. Okay? Where have we seen something like this before? In our substitution and our elimination reactions. Okay? So if we started with an SN1, if we break one bond, then form the other, so we do them in a stepwise system, we ended up with 2 possible products out of that. Right? If we looked at the SN2, where we did it all at once, just combined all those 2 things at one individual instance, we ended up with 1 product. Okay? That's going to drastically change our overall results. And if I'm going to run the Diels-Alder reaction, I'd like to know what I get out of it. To know that, I have to understand something about the mechanism, and that's going back to deciding between these 2, what's the results. Okay? Before we even approach both of those mechanistic possibilities, we need to go through and simplify our argument. Okay? One of the big issues, and I know simplify sounds kind of crazy at this point, but it is simplifying it. Okay? One of the big issues with alkenes, and we saw this with addition reactions as well, is that we're reacting a p orbital. Well, where are the electrons in a p orbital? They're above and below the plane of atoms, which means there are 2 possible ways an alkene can react. It can react by picking up electrons or sending its electrons above the structure or below it. So if we go through and take a look at our Diels-Alder reaction, what I've got lined up here is a similar situation with our p orbitals and trying to match these up. You'll notice in one case, we've got the sigma bond forming on the up face of our diene, and other case, we've got the sigma bond forming on the down face of the diene. Okay? I went through, showed all those orbital overlaps to see how we could potentially form it, and we end up with those 2 possible products. Are those products different? Okay, I like the kind of sound coming out of that, okay, at least initially. No, I would say right away just based on what atoms are shown on there. However, look a little bit closer. That carbon is red. Are these structures still actually the same?
No.
No. If we tried to overlap them, that red carbon does not overlap, which means they aren't identical. The actual relationship is enantiomers. They're stereoisomers. Okay? So when we look at the Diels-Alder reaction, this holds true even once we identify the mechanism. We're going to end up with at least 2 products every single time. Okay? The relationship between those 2 products may be that they're identical, but in most cases we end up with enantiomers or diastereomers or other fun things to worry about. Okay? Because we want to simplify this, I don't want to have to go through and show here's the sigma up reaction and the sigma down reaction in all cases. You'll notice the textbook does the same thing. They just don't tell you that they're skipping one of them. Okay? Which one do you think we should look at? I actually don't remember. They both look roughly the same to me. We're going to take a look at the sigma down. Why do the sigma down? Really simple reason. I think I can draw that better. Okay, so the sigma down to me looks a little bit cleaner than the sigma up version. I can see those atoms a little bit better for drawing that out. Okay, so in the DA1, what did we say? Stepwise or continuous or simultaneous? Stepwise. So one unimolecular, I tried to match them with the SN1 versus SN2. Okay, so we're going to go with the SN1 as stepwise. So we're going to form one bond first. To show that, we're going to take our pi electrons from our diene and share them with our dienophile. Why have the diene share its electrons and not the dienophile? Why is it the nucleophile? You're right. Which structure has more electrons? The diene, because it has 2 pi bonds. Okay? If you're trying to decide between 2 atoms, which one's the nucleophile, which one's the electrophile, okay? Nucleophiles have more electrons. It makes sense to have the diene act as our nucleophile. So that's why the arrow is showing that. We're now showing that orbital overlap with that back bond, okay, forming that connection. You'll notice that I've got a dashed line on the front face. Okay? That dashed line is not an actual bond forming, but showing that that's where our bond will form. Okay? The big issue with the DA1 mechanism is that if we simplify and pull all those p orbitals out of the way, we end up with this situation. So it's a little bit cleaner. This bond is what type of a bond? What can sigma bonds do? Rotate. Which means before I actually close that structure off and form that second bond, I have the potential for rotating it, and I generate 2 products. What's the relationship between these 2 products? Actually, in this case, they're diastereomers because of that red carbon. Okay? So we end up with 2 products in the DA1 mechanism. I'm kind of running out of time, so we'll jump to the DA2. In the DA2, we'll go through and we'll form this all at the exact same instant. If we go through and form it all at the exact same instant, can I do that rotation? No. Why not? It is simultaneous, but that's not going to necessarily prevent the rotation. It's a ring. Rings can't rotate about those sigma bonds, okay? At least at this level. Okay? We could go through and do chair flips, but that's not going to change our product. The product will still be the same. You've noticed I've gone through and added these A, Bs, and Cs. Why would I do that? Okay, those of you in lab might remember. Without those A, Bs, and Cs, can we tell the difference between our products? No. Okay, so we include the A, B, and C so that we can actually start to predict something about the arrangement of these. So how do we decide between these 2 mechanisms? We go into the lab and we attempt to solve it. So we pick some structures that can reflect this and show this. Okay, so we'll run experiment 1, where I'm using a what type of dienophile? Cis or trans? It's a cis alkene, and I react that with my diene. The result I get is this structure. Okay? Those 2 groups end up on the same side of the ring. Which mechanism matches that? Matches that. DA2. We only end up with 1 product. But maybe that's an artifact of just having the cis alkene. Okay? So what should we do? Try it with the trans and see what happens. So we crank it out with the trans. What do we end up with? Trans product. Which mechanism? DA2 again. When we look at the Diels-Alder reaction, it is a concerted reaction, meaning it happens all at the exact same instant. Okay? There is no stepwise process. Everything happens at once, which means the stereochemistry or the regiochemistry of our starting materials is maintained in the product. Okay? I had expected to get further, but I did not. So